So the next type of differential equation. So the derivative is simply some function of y. So just a function of y by itself. So something like that. Well, something like that we can easily separate and rewrite it as dy over gy is equal to dx. So it's quite easily handled. By the way, you could also think of it as a first order linear, because I could rearrange that equation and end up with dy dx minus g of y is equal to function x. Function x just happens to be 0. So you could consider it that way as well. Here's one, which I hope looks familiar. Do you recognise it? Anyone? Yeah, it was our modified growth and decay equation. Remember, we said when we see this one, we can just quote the answer. Let's go see where it comes from though. So dy dx is some constant outside of y minus n. So if I separate the variables on this one, I'll end up with dy on y minus n, and I'll move the k over with the dx. And I've made it a definite one because they've told me, remember the initial conditions were that the initial population was n plus a, we said. So I've made it n plus a there. So log of y minus n is equal to kx. Also, remember when you're doing the integral just from 0 to x of dx or something like that, you can just bang, put x straight down. I mean, it's kind of trivial, the working out on that one. Okay, so kx is the log of y minus n over a. Exponentialise both sides. So e to the kx is the absolute value of y minus n over a. So y minus n is a e to the kx, and we end up with, you'll hopefully recall, what we would just quote as the answer for our modified growth and decay. So y is equal to n plus a e to the kx. But anyway, that's proving that what we have been quoting for that we can use. So dy dx is e to the power of 2y minus 1. So separate it out. The right hand side will just be x plus a constant, because again we're just saying integral of dx. Left hand side we'll get minus half e to the 1 minus 2y. So a bit of manipulation to get there, but eventually we can make y the subject. So I guess the trickiest bit of this is just the algebraic manipulation. You just got to be careful with moving terms from side to side and things like that. So we get half 1 minus the log of whatever that constant is, minus 2x. Square root of 1 minus y squared. Which one's that? A square root of 1 minus y squared. That's inverse sine? Yeah. Or negative inverse cos if you prefer. So inverse sine of y is x plus a constant. So y is sine of x plus c. We're now going to look at the very specific type of equation called the logistic equation. It's a first order differential equation. It's in this form. Now don't panic, we don't look at really complicated ones of these, but technically anything in this form is a logistic equation. So the derivative of some function x with respect to x is function x times 1 minus function x. Now, for our course, the function x is going to be, well, in this case function y, sorry, because it's the y dx. So y and some p minus y. It might not be 1 minus y, could be some other number. But pretty much we're limited to that particular logistic equation. So let's solve it. Let's make that p equal to 1. And the initial condition we're going to have for this one is that it will be a, whatever a is. Now, there's our slope field. So we look at that first before actually doing any integration. Now you can see, depending on where the point that you know is, what type of curve you get. So remember, we're saying y naught is a. So if I started with a being a negative number down here, my slope field is going to turn me to a horizontal asymptote at the, that's the x-axis, isn't it? Yeah. So at the x-axis, we'd end up with some sort of, I was going to say hyperbolic, but quite possibly it's more likely to be an exponential than a hyperbola there. But it's going asymptotic. And if a was bigger than 1, again we're going to end up with a horizontal asymptote, and it's around about, where's that? Where's my scale? There's 2. So it looks like that's at about 1, doesn't it? So if a is bigger than 1, we'll end up, well that makes sense, if a is bigger than 1. So yes, the horizontal asymptote's at 1. But again, we get similar sort of shape coming down asymptotic. If it's in between 0 and 1, so if we start somewhere in the middle, we get Well, that's similar to what sort of curves we've seen like that? Inverse tan, that sort of curve it looks like. I mean, it's not an inverse tan curve, but it's got that sort of shape. There are two other solutions there though. There are two trivial solutions, those two asymptotes if you like. Because if we made A equal to 0, well, but look at the slope field. If initially it's at 0, but 0 was the horizontal asymptote, which means all those little tangents we're drawing in are all horizontal. So if I'm starting at 0, it's going to send me horizontal. So I just get that straight line. And same as when we're at 1, we'd get the straight line there. So the asymptotes often turn out to be just trivial solutions to the problem. So there's actually 5 possible answers for this one. Okay, separate the variables. I get dy on y, 1 minus y, is equal to dx. So the right-hand side's nice and easy. Now, using partial fractions, I can turn the y of y, 1 minus y, into 1 on y plus 1 on 1 minus y. And that will integrate to give the log of y minus the log of 1 minus y, which I've put together into one integral. Sub in the y, sub in the a, and then exponentialize both sides. And so ae to the x will equal y on 1 minus y. Now basically a is going to equal a on 1 minus a, but rather than carrying this fraction all the way through, because a on 1 minus a is just a constant, because a is a constant. So I'm saying the absolute value of a is a on 1 minus a. So I'm now calling it capital A. Now we're trying to make y the subject. So rearranging that, and we eventually end up with ae to the x on 1 plus ae to the x. Now I'm going to play around with this one as well. It becomes useful in some further calculations. So I'm going to divide everything by ae to the x. I'm going to divide everything by ae to the x. So we would end up with 1 on the top of the fraction, and then on the bottom of the fraction, 1 over 1 on ae to the x. Well, that becomes e to the negative x, and rather again having a fraction on a fraction, 1 on a, well that's also a constant, which I'm now calling b. And then ae to the x divided by ae to the x would be 1. So we end up with 3 solutions. Our 2 trivial solutions, and our solution 1 over be to the negative x plus 1. So part 2, find any inflection points. So we know that inflection points happen when the second derivative is equal to 0. Now, second derivative is the derivative of the first derivative. I'm going to do this by implicit differentiation. Differentiate y, 1 minus y with respect to y, times it by dy dx. And I end up with y, 1 minus 2y, 1 minus y. We want the second derivative equal to 0. So I've got 3 possibilities. Y is 0, a half, or 1. Now, I'm not going to now work out the third derivative to test these. I can go back to the slope field and just have a look at that to see what's happening. Because we know, well, it's not going to be y equals 0, because that was just a horizontal line. No inflection point there. It's not going to be y equals 1. There's no inflection point there. Y equals a half, not a problem. There was an inflection point round about there if you look at the slope field. So the only possible inflection point is when y is equal to a half. So if I now go back to that, where was it? B, there it is. So we're saying y is equal to a half. So be to the minus x is equal to 1. Okay, so there's the lovely point. The log of 1 minus a to a half. All right.